Hi, so my name's Cole. So I want to sort of just quickly blast through what I've been doing of late while this whole crisis is going wherever it's going. Sorry, excuse me. So this is we've been well, I've been developing a motor control algorithm. So this is the work area. So here's my laptop over here. Here's some C code over here. And here's the hardware. So let me just move this laptop out the way so we can see what's going on. We're very limited for space over here. So here's the motor controller, the processor board basically. So this is a Texas Instruments AMS, 6548. So it's a multi-core processor. It has several processors on there. About 8 or 9 or whatever it is. But I'm just using the single one at the moment, which is A53. An extremely powerful board. If you compare this to a PLC, this is like it's day and night basically. This PLC is quite blunt if you compare it to this one. This is a real-time operating system on there. So I wrote a space vector PWM, which is a type of modulation algorithm to drive a motor. So we're using a volts frequency algorithm. So we basically keep the volts frequency at a fixed ratio of 4.4. So we're driving some digital outputs over here via a serial bus over here, which is I2C, which is typical of this environment, not the PLC world, although we could develop EtherCAT connections on this and Ethernet IP and all the rest of it. At this level, we could do that quite easily. In fact, this could become a PLC, this board, as you see it. But anyway, let's not talk about that too much. So we drive the digital output. So we come to this variable board over here. So we've got some optocouplers over here. This is obviously to isolate the processor side from the power, from the mains chopper section, the power module, because we don't want things blowing up basically. So this is an open collector on this IC over here, driving a transistor and switching 5 volts over this ribbon cable via this ribbon cable here. So we have this connection over here. So this is parallel connection over here, and that drives the low side on the switching of the hex bridge. There's a high side, and there's more isolation here. Although there is isolation in here, but let's not talk about that too much. But this isolation of this power supply here, this 24 volts, is isolated from the DC bus. So the DC bus at the moment is 30 volts. It can be 600 volts. Can switch 75 amps on this device. There's your break-in transistor. So in other words, you get regen on DC bus. We can dissipate the energy via a brake resistor. Don't need this at the moment. Is the motor supply, so it's RST or UVW, L1, L2, L3, whichever way you want to call it. Going to our motor here, 3-phase polyphase induction motor, asynchronous, 120 watt delta connected, and there's the nameplate of it. There we go. So it's just perfectly adequate for what I'm doing over here, because the control algorithm can work on a small motor or a big motor. It's all dependent on the size of the power device, really. So this is about, I could probably haul 30 kilowatts out of this at the moment. Well, when I get the DC bus, that is full capacity. But anyway, so coming back to this variable board over here. So here's a current transformer. So this is quite a special current transformer. It's not your run-of-the-mill type. So this is a Hall effect transistor in it. So in other words, we can measure DC current in it, which is not typical of a CT. So this needs a 12 volt supply. So I've had to build this variable voltage supply over here. So this is an LM, whatever it is, 318 or whatever. So 24 volts in, and then I get 12 volts out to power that up. So this is the primary side on the winding, and obviously this is a secondary core over here, the blue bit over here. So we get volt signal out. Volt signal is going to this header connection over here. Then the header connection essentially will end up onto these pins over here, which is the A to D converter. So this is a 12-bit A to D converter. Yeah, sampling rates, yeah, several hundred kilohertz basically. So it's very, very fast. Like I said, this is real-time operating system. It's has very strong similarities to a PLC, but is a very sharp tool, as opposed to a PLC, which is sort of a bluntish tool in comparison. Yeah, obviously a PLC has its place, but not in this type of algorithm. This is not the place for the PLC. This is a place for real-time operating systems. So that's where we're at. At the moment, I'm going to be testing this Hall effect CT over here. So I'm going to be reading some current via the primary. So I'm going to do this by injecting a DC voltage into the stator winding, and then I'll do some calculations over there, and I'll calculate the resistance of a single winding in the stator. So this says, like I said, delta connected. So there's another calculation there, converting from delta to work out the single phase resistance. Also, I'll be working out the inductance of this motor. So that's LS, and we'll do that by working out the rate of change of current. Okay, so the rate of change of current should give me an indication of the stator. So from that we can obviously work out the impedance of the winding. So this is where we're at, and the reason I'm going to do this is because this is a volts frequency algorithm. So I've had that turning at 100 RPM on the volts frequency algorithm, 100 RPM, because we have limited bus capabilities. But like I said, we want to work these parameters up because we want to use more sophisticated algorithms. So we're going to use like a field-orientated control or direct torque control algorithm, and we need to get the motor parameters. Okay, and this is not typically given on the nameplate, or certainly not on this motor. Okay, and the motor's made in China, so I think I might have some issues trying to get these parameters from them. And obviously this nameplate is, as accurate as you want to believe it. It's probably not very accurate, or like I say, so that's why we needed to get the motor model correct. All sort of quite rough and ready, because this keeps changing several times. I've used these jumper cables so you can sort of pull things out and in, so it's quite handy. It saves me desoldering and soldering and unwiring it too much. So that's where we're at. So thanks for listening, and yeah, I hope you enjoyed, or as much as you can see. But yeah, thanks and good luck.